Hi, welcome to section 12.2 notes on chords and arcs. So first of all, if you look in the top left-hand corner, a chord is a segment that has both endpoints on the circle. So you can see here, chord AB has A and B on the circle. A diameter is actually a special chord that happens to go through the center of the circle as well, but a chord does not have to be a diameter as long as both endpoints are on the circle. If you look to the top right, arc AB is just the curved part of the circle, again, between 2 points on that circle. We can have minor arcs and major arcs that we talked about in section 10.6. A minor arc you're going to name with 2 letters, and you're going to go the shortest distance between those 2 points. And a major arc that is either half the circle, which would be a semicircle, or more than half the circle would be a major arc, and you name it with 3 letters, and those 3 letters kind of force you to go the longer way instead of the shorter way. All right, so now we're going to go over some different properties regarding chords and arcs. You can see to the right here, kind of the central theme going on here is that central angles are congruent if and only if. That's what the IFF stands for. We talked about that earlier in the year. If and only if arcs are congruent, if and only if chords are congruent. So again, if one is congruent, one piece of that is congruent, you know the other pieces are congruent as well. So that is what these different properties are going to go over. So it's going to tell us a property, and then we'll say an example of it based on the picture that we see. So the first one is on central angles and arcs. So it says central angles are congruent if and only if arcs are congruent. And that if and only if means that basically that statement and its converse are both true. Central angles are congruent if and only, if arcs are congruent, and if arcs are congruent, then the central angles are therefore congruent. So an example specific to this picture would be if angle AOB is congruent to angle COD, then arc AB is congruent to arc CD. Okay, and the converse of that is also true. So instead of writing out the converse, I'll just say converse also true. Where, again, if I wrote that the other way, if I said if arc AB is congruent to arc CD, then angle AOB is congruent to COD, that would also be true. All right, the second one we can see is about central angles and chords. So this says central angles are congruent if and only if chords are congruent. So the specific example that we have here is if angle AOB is congruent to angle COD, then we know that segment AB, which is a chord, must be congruent to segment CD, which is another chord. Okay, and again, the converse of that statement is also true, instead of taking the time to write the whole thing out. All right, next up is on chords and arcs. So this one says chords are congruent if and only if arcs are congruent. So again, if we know that two chords are congruent, we know the arcs that intercept those 2 chords must be congruent also. So the specific example we have here is if segment AB, which is a chord, is congruent to segment CD, then arc AB is congruent to arc CD. All right, and again, same thing as the converse is also true. All right, next up says the chord is equidistant. And we talked about the term equidistant earlier in the year. We said it means equal distance, so not too hard there. So in this particular case, let me plug in my computer here. Okay, so in this particular case, it says the chord is equidistant from the center if and only if the chords are congruent. So Again, it's showing me here that PQ, segment PQ is congruent to segment RS. So if we know those two chords are congruent, then we basically know that both of those chords must be the same distance away, the same right angle distance away from the center of the circle, and that's what that is showing. So again, I can say that if segment PQ is congruent to segment RS, then segment AO, which is the part that is equal distance from the chord to the center, must be congruent to segment OB. Okay, and again, the converse of that would also be true. Okay, and then last one here is perpendicular bisectors in a circle. So it says here a diameter is perpendicular to a chord if and only if the diameter bisects the chord in its arc. We've talked about bisect a lot this year. Bisect means cuts in half. Diameter, again, is a segment, or technically a chord, that goes through the center of the circle. And perpendicular, we know, means it forms a right angle. So in this case, it's saying that a diameter, which, in this case would be CD, if it goes to the center of the circle E, a diameter is perpendicular, meaning it forms a right angle, to a chord if and only if the diameter, which is CD, bisects the chord and the arc, or cuts the chord in half, which you can see by these two congruent marks, and cuts the arc in half, which shows these two pieces congruent. Okay, so again, the specific example I can say here is if segment CD is a diameter and CD, that diameter, is perpendicular to AB, then segment AE is congruent to segment EB, so both pieces of that chord, and arc AC must be congruent to arc CB. Okay. All right, so that's it for the properties. Now we're going to use some of those to solve on the next page. So on the next page, it says that circle X is congruent to circle E. And what can we conclude from that? So there's a lot of things we could say from that. But if we know the two circles are congruent, we basically know that the radius is the same for each circle. That's what makes a congruent circle. But some of the things we could say about it then is that if we know that two circles are congruent and they're already showing me that this piece is congruent to this piece. So I could say that, but it's kind of saying what else can I conclude besides what's in the picture? So I could also say that arc PQ must be congruent to arc AB. Okay. I could also say that angle PXQ is congruent to angle AEB. Okay, so I basically just said, that this arc is congruent to that arc. I also just said that this angle is congruent to that angle. And yeah, that's all I have to say, but I could say some more. I also know that this angle over here has to be congruent for both because those are vertical angles. So I could go on to say angle SXR is congruent to angle DC. Okay, from that, I could go ahead and talk about, those two segments right there. I could say SR is congruent to DC. And I could also get into these arcs, this arc and this arc. I could say arc SR is congruent to arc DC. Okay, so it's really a lot I can say there. Again, you can try number 2 if you want to pause the video and try it, or you can just do it with me. But again, same idea as or similar idea to what we just said. In this particular case, we know that These arcs are congruent that we can see in the picture. So therefore, we know that these two chords must be congruent. So we can say WY is congruent to DF. And we can also talk about these angles that must be congruent. So we can say angle YXW must be congruent to DEF. All right, so moving right along. Now, some of these are pretty quick. If you look at number 3, it says, what is X? And X is referring to this whole length from here to here. So we see these two pieces are congruent, that they're both 3. Then we know that these two chords must be congruent. And if this piece is 8, and there's a congruent mark here, that piece is 8. So we know that whole thing is 16. So since these two chords are the same distance away from the center, then X has to be 16 as well. Okay. On number 4, we can see that, these two congruent marks are the same as these two congruent marks. So we know this whole chord is congruent. The two whole chords are congruent. So therefore, they must be the same distance away from the center. And if we can already see that one is 5, then we know that that has to be 5 also. Like I said, these are pretty quick. Some of them you don't even have to work out. All right, on number 5, we can see that these two pieces are congruent here. So we know that they're the same distance away from the center of the circle. They're both 4.9 away. It's asking what X is, which is this whole length. And we can see that 6.3 is referring to this piece. So we know this piece is also 6.3. So we know the whole thing then has to be 6.3 plus 6.3, which is 12.6. And if we know this one's 12.6, we know up here has to be 12.6. All right, next, on number 6, here's where we need to do a little bit of work here. So if we look at this on number 6, they want us to figure out what X is. From the center to the chord is X. I do see if there's a right angle here, that has to be a right angle as well. Okay, I do know if this whole thing is 14, then this piece is 7 and this piece is 7. I also know that if this whole diameter is 18, then this must be 9 and this must be 9. So really what I'm looking at, if I kind of focus on the triangle where the X is, I basically have a right triangle, and this piece is 7, that piece is X, and that piece is 9. And I can use Pythagorean theorem to figure that out. 7 squared plus X squared is equal to 9 squared. So 49 plus X squared is equal to 81. When I subtract 49 on each side, I get 32. And when I take the square root of each side, I try and think of what perfect square goes evenly into 32, and the biggest one is 16. Goes in 2 times. So then I can reduce that down. Square root of 16 is 4, so it comes outside the square root. I can't take the square root of 2, so it stays in. And that's what we get. Okay, if we look at number 7, here they're giving me the distance from the center of the circle out to the chord. They're telling me that this whole length from here to here is 10, so I know I've got 5 here, 5 here. And I don't see the right triangle here, but keep in mind, this is the radius, and I can move the radius anywhere I want to. The radius goes from the center out to the circle. So if I want to move it over here so that I have, that's not a very straight line, so that I have a right triangle to deal with, I can do that. And I know that length would be X, which is what we're looking for anyways. So basically, I have this right triangle, and X and 4.2 and 5 are my dimensions. So if I plug that in the Pythagorean theorem, I've got 4.2 squared plus 5 squared is equal to X squared. So I get 17.64 plus 25 is equal to x squared. And then I've got 42.64. And if I go and take the square root of both sides, I end up with x equals 6.5. All right, and last but not least, they are asking me what x is, which is this whole length. But I see a right triangle there. I'm just going to go ahead and call that piece y for right now. I'll call that y and that y. So if I go and use the Pythagorean theorem, if it helps you to do a right triangle, I've got 15, y, and 8. So if I go y squared plus 8 squared equals 15 squared, then that gives me y squared plus 64 is equal to 225. Y squared, if I subtract 64 from each side, I get 161. And if I take the square root of both sides, I end up with 12.7. Or if I want to go ahead and just leave it as square root of 161 to keep it more accurate, I can do that. All right. Now I want to figure out what x is, which just means I need to double this. If I go 2 times square root of 161, then I get the 25.4. And that's it for section 12 too. Let me know if you have any questions.